Close your eyes for a moment. Imagine stepping into a sauna. That immediate wave of warmth washes over you, the dry air embraces your skin, and you feel that deep anticipation building, perhaps the invigorating rush of loyalty just around the corner. It's a profound experience, isn't it? Deeply rooted in culture and personal well-being.
It really is. Very primal, in a way.
But have you ever stopped to think about what's actually happening in there? From a purely physical thermal perspective? How is that intense enveloping heat created and maintained?
It's a great question. Because it feels simple, but the physics behind it, not so much.
So today on The Deep Dive, we're embarking on a journey into the fascinating world of sauna physics. You sent us a stack of sources, articles, research, even some of your own notes. And our mission is basically to extract the most important nuggets of knowledge and maybe some surprising facts.
Yeah, to distill it down.
Exactly. We want to give you a comprehensive, easily digestible understanding of the thermal dynamics at play. We're trying to go beyond just the sensation to, a truly informed appreciation.
Moving from feeling to understanding.
Right. You can expect to explore the fundamental principles of heat, unpack how saunas warm up and stay hot, dive into the captivating science of steam loyalty, uncover critical ventilation strategies, understand the material science that keeps you comfortable and safe, hopefully.
Hopefully, yes. Safety's key.
And even glimpse into the future of sauna design. Prepare for some real aha moments, all delivered with, hopefully, a clear structure that respects your time.
Okay, let's unpack this. What's truly remarkable, I think, is that even something as seemingly simple and ancient as a sauna involves incredibly complex physics, often far more intricate than we usually imagine.
Indeed, and our sources today beautifully illuminate these principles. We're going from the very definition of temperature, a concept we often take for granted, right through to the nuanced interactions of various heat transfer modes within this unique controlled environment. It's testament to how much science underpins even our most cherished rituals. Okay, so let's start with the absolute basics, because really understanding these foundational concepts is like getting the secret handshake to everything else we'll discuss. We're talking about the very definition of temperature. It's more than just simply hot, isn't it?
Absolutely. Yeah, fundamentally more. Physically speaking, temperature is a property that allows us to define a common scale for how hot or cold something is. Think of it like this.
Yeah.
You have a hot sauna, and you put a thermometer in it.
Right.
And maybe you put a cup of water in it. Eventually, both the thermometer and the water, they reach the same temperature as the sauna air, and maybe even you, the bather.
Yeah.
We say they're all in thermal equilibrium.
Equilibrium, okay.
This idea, often called the zeroth principle of thermodynamics, it's the fundamental reason thermometers actually work and give us a consistent measure of heat. It's about reaching a balance.
So it's about balance, things eventually reaching the same thermal state. But what's happening at that tiny invisible level, like the molecules?
Yeah, good question. At the microscopic level, temperature is directly proportional to the average kinetic energy of a system's particles. We call this thermal agitation. Imagine all the tiny molecules or atoms, in the air, in the wood, in your body.
They're all moving.
They're constantly jiggling, vibrating, colliding.
Mm.
The more rapidly and energetically those particles are moving, the higher the temperature we measure, and, well, the hotter it feels to us.
So more jiggle equals more heat.
Pretty much. And when we talk about absolute zero, that's 0 Kelvin, or about minus 273 degrees Celsius.
Yeah.
At that point, particles are at their absolute minimal agitation speed, not completely motionless because quantum physics gets involved.
Right, quantum uncertainty.
Exactly. But heat transfer essentially ceases at that point, is the theoretical floor.
Okay, here's where it gets really interesting for me and maybe a little mind-bending. How do you even define temperature in the vacuum of space, where there are hardly any molecules to measure their jiggling? It seems impossible.
That's a fantastic question, and it really highlights how we have to expand our understanding of temperature beyond just jiggling molecules sometimes. In the vacuum of space.
Wow. So whether it's the jiggling of molecules or the balance of absorbed and emitted radiation, understanding this foundational concept of temperature is truly key. It helps appreciate how heat functions within the enclosed, controlled environment of a sauna. It's not just a blanket of warmth, it's a very specific energetic state that's constantly being managed.
Precisely. And once we grasp what temperature fundamentally is, we can then appreciate how that heat actually moves from one place to another, how it gets transferred.
Which brings us to the 4 fundamental modes of heat transfer. I like to think of them as the thermal orchestra of the sauna. It's not just one thing making you warm in there, is it? It's a mix.
No, not at all. You're spot on. The entire thermal experience in a sauna is a complex interplay of four distinct modes: conduction, convection, radiation, and phase change. Each plays a critical and often surprising role. They all contribute to the overall thermal experience that makes a sauna so, well, unique.
Let's break them down. First up, conduction, which I always think of as the slow, steady crawl of heat through solid stuff.
That's a very apt description. Yeah, slow and steady. Conduction is how heat spreads through direct molecular contact. Imagine a line of dominoes. Energy is passed from one particle to the next through direct collisions without any bulk movement of the matter itself.
No flow, just bumping.
Just bumping along.
Oh.
It's a relatively slow process, and its rate depends on how easily the material allows this energy to pass its thermal conductivity.
So what does this all mean for our sauna walls? Think of it like that ripple effect at the molecular level, gradually transferring energy through the wood and insulation. That's how heat slowly permeates and eventually tries to escape the sauna through its solid walls, right? Even if those walls are well insulated.
Exactly. The better the insulation, the slower that crawl, the less heat you lose that way.
Okay. Next, we have convection, where heat is actually carried by flowing fluids, air, in the sauna's case.
Yes, this one feels more intuitive for a sauna, with all that hot air moving around.
Definitely. Seems like the main event.
It is indeed a major player. Convection involves the transport of heat by the actual movement of matter, specifically fluids, which can be gases, like the air in a sauna, or liquids. We see two main types: natural convection.
Hot air rising.
Exactly. Driven by temperature differences that create buoyancy, hot, lighter fluids rise, while colder, denser fluids sink. This is the primary driver of air circulation in a traditional sauna, the engine of the airflow.
And the other type?
Then there's forced convection, where fluid movement is actively caused by external means, such as fans, pumps, or even manually waving a towel, or using a Vita or Venic in some sauna traditions.
Ah, interesting. So stirring the air counts.
It does. And sometimes you get a mix of both natural and forced convection happening at the same time. In a sauna, hot air heats up by the stove, rises, and transfers its energy to colder surfaces like the walls, or, crucially, to the people inside to you.
And the rate at which convection transfers heat can be dramatically different depending on the situation, right? Like wind chill.
Absolutely. Think about standing in a still room versus standing in front of a fan on a hot day. That's the difference between natural and forced convection in action. Convection is significantly more efficient at transferring heat when the air or liquid is moving faster.
Got it.
In a sauna context, ventilation systems, which move fresh, cool air in and hot, stale air out, are prime examples of using forced convection, constantly managing the air temperature and quality.
Okay. And then there's radiation, which always sounds a bit mysterious because it doesn't need a medium, like heat from the sun reaching us through space.
That's a great comparison. Yeah, radiation is fascinating. Heat travels as electromagnetic waves, quasi-instantaneously at the speed of light. It requires no physical medium, meaning it can pass through vacuums like space and transparent gases like dry air.
So it cuts right through the air in the sauna.
Mostly, yes. Unlike conduction and convection, it's also highly nonlinear, meaning a small increase in the temperature of a radiating object can lead to a disproportionately large increase in the amount of radiant heat it emits. It scales with temperature to the fourth power, which is huge.
Wow.
In a sauna, the hot stove stones and the stove structure radiate heat directly to cooler surfaces, like the walls and benches, and importantly, to the occupants. While the air itself is mostly transparent, the steam from l'oily can make it somewhat opaque to radiation, adding another layer of complexity we can maybe touch on later.
I found a surprising fact in our sources about radiation. It isn't just for high temperatures. It can be as important or even more important than convection for a resting human at like normal room temperature, around 20 degrees C. So it doesn't take extreme heat to make radiation a significant factor in how we feel warm or cool.
That's a crucial point, yeah. And it helps explain why you can feel warm sitting near a sunny window even if the air isn't hot, or feel the cold radiating from a cold window in winter, or even feel the warmth from a person across a room. In the sauna, radiation is critical for homogenizing temperature. Without it, natural convection alone would create a much steeper vertical temperature gradient, very cold near the floor, scorching near the ceiling. Radiation helps even things out by sending heat directly across the space, bypassing the air sometimes.
Makes sense. It balances things out. Okay, finally, we have phase change, the hidden heat of steam. This one is directly linked to the l'oily experience, right? This is where the magic happens.
Absolutely, and it's pure, powerful physics. This mode is critical for understanding that intense sensation of loyalty. When a substance changes its state, for example, liquid water turning into water vapor, or vapor turning back into liquid, it either absorbs or releases a significant amount of energy known as latent heat.
Latent meaning hidden.
Hidden, yes. Evaporation absorbs energy, causing cooling. Think of sweat evaporating from your skin, cooling you down. But condensation releases energy, causing heating.
Okay, so how does that work with loyalty?
In a sauna, when water is thrown onto hot stones, it rapidly vaporizes, absorbing a substantial amount of energy from the stones. Then this steam, this water vapor, being lighter than air, rises and travels until it hits a relatively cooler surface like your skin, which is typically around 40–44 degrees in a sauna.
And then,
On your skin, it condenses back into tiny water droplets. And in doing so, it releases that massive quantity of latent heat directly onto your skin. The rate of heat transfer during this condensation can be enormous, thousands of watts per square meter, much higher than simple convection, which is why limuli feels so incredibly intense, like a sudden, powerful burst of warmth.
wow. So it's not just hot or air, it's the steam turning back into water on you.
That's the main driver, yes.
Yeah.
If we connect this to the bigger picture, these four modes, conduction, convection, radiation, phase change, they aren't just theoretical concepts working in isolation. They're constantly interacting within the sauna, working together. It's a symphony of thermal processes, really, shaping our entire experience in ways that are often surprising and sometimes even counterintuitive.
Right. It's a dynamic system. Okay, with those fundamentals in mind, let's zoom in. Let's explore how a sauna actually heats up and, maybe even more importantly, how it manages to stay so wonderfully hot. At the heart of it all, literally, is the stove.
Indeed, the stove is truly the heart of the heat. Whether it's a wood-burning stove using pyrolysis, the thermal decomposition of wood, or an electric stove generating heat through the Joule effect, its primary function is to generate heat. That heat first warms the stove structure itself and the stones within it, primarily via conduction, solid to solid.
Okay, then the air gets involved.
Then, the air in direct contact with these hot surfaces heats up by convection.
What's fascinating here is how the sauna air naturally organizes itself. We all know that hot air rises, but how does that create a system within the sauna? It's not just random swirling, is it?
No, it's quite organized, actually. That's natural convection in action, and it's a beautifully efficient system. Hot air is less dense, so it rises, displacing cooler, denser air, which then descends to replace it near the stove. This creates continuous natural convection loops within the sauna.
Like a conveyor belt of heat.
You can think of the stove as acting like a thermal pump. It draws cooler air from the lower parts of the sauna, heats it efficiently, and then releases that warmer, lighter air at the top. This continuous circulation is fundamental to the initial heating process and also helps maintain temperature distribution later on.
And the stove isn't just heating air by contact, it's also radiating heat directly, isn't it? That's the heat you feel directly on your skin from across the room, even if the air between you isn't that hot yet.
Yes, very significantly. The hot structures of the stoves and the stones radiate heat directly to cooler surfaces, including the walls, benches, and, most importantly, to the people inside. This radiant heat transfer occurs quasi-instantaneously at the speed of light, and remember, it's highly nonlinear. If the stove gets just a little bit hotter, it radiates a disproportionately larger amount of heat.
How much radiation are we talking about?
Well, our sources suggest that stoves can emit a significant portion of their total power as radiation, often maybe 30, 40, up to even 75% in some estimates, though 75 might be high. The rest is through convection. Regardless of the exact split, radiation is a profound and impactful phenomenon in sauna heating, crucial to that feeling of enveloping warmth.
I can imagine that intense direct radiation, especially from a super hot stove, might not always be comfortable, like standing too close to a bonfire. How do designers address that?
You're right. Intense or uneven direct radiation can be quite uncomfortable, almost prickly. That's why modern stove designs often incorporate features like a double skin. This additional layer, sort of a shield, helps reduce direct radiation and, importantly, increases convective air movement around the stove, leading to more uniform and, well, pleasant temperatures throughout the sauna space.
So distance matters.
Absolutely. For optimal comfort, a minimum distance of about 90 centimeters, roughly 3 feet, from the stove is ideally recommended to mitigate that direct, intense radiation. Gives it space to mix.
So the heat from the stove radiates outwards, heating everything else in the sauna. The walls, the benches, they soak it up.
Precisely. The radiation from the stove heats all the surrounding structures. the benches, walls, floor, and ceiling. These structures absorb that radiant heat, conduct it inwards into their material, and then they can transfer heat back to the sauna air by convection if the air happens to be cooler than the surface.
So the walls can heat the air too.
Yes, it creates a complex, dynamic heat exchange. For example, the ceiling and upper walls, being hotter due to air stratification, actually act like secondary radiant panels,
Yeah.
gently emitting heat downwards to occupants and lower structures. It's a continuous, multi-directional flow of energy. It's not just stove to you.
Okay, this raises an important question that might seem a little counterintuitive. Why aren't the absolute hottest surfaces always receiving the most heat? I would think the closer and hotter something is, the more heat it gets, period.
It does seem counterintuitive at first, but it comes down to a fundamental principle. Heat flux, which is the rate of heat transfer, depends primarily on the difference in temperature between objects and also how well they see each other radiatively.
The temperature gap?
Exactly. Imagine a surface at 95 degrees next to a 100-degree C source. The temperature difference is only 5 degrees C, so it will receive only a relatively small amount of heat flux, maybe 25 watts per square meter. However, a much colder surface, like human skin at around 44 degrees C, or even a non-insulated window at maybe 60 degrees C, has a much larger temperature difference with the hot stove. Consequently, it will receive a very significant and noticeable amount of heat flux, maybe 300 to 600 watts per square meter.
Ah, so my skin being cooler actually draws more heat towards it than a hotter wall nearby.
In terms of flux density, yes. Even a well-insulated wall very close to the stove might reach a high temperature, say 150 degrees C, and receive a lot of local radiant heat flux, maybe 420 Willer-Suter. But because it's already so hot, it transfers most of that heat back to the cooler sauna air by convection, and only a tiny portion, maybe 20 Willer-med, actually escapes to the outside through the wall. So it's about the gradient, the temperature gap, and where the heat can most easily go.
And does humidity affect radiation as well? Does steam change things?
Yes, the presence of water vapor in the air, especially during loyalty, can make the air partially opaque to certain wavelengths of infrared radiation. This means the air itself can absorb and re-emit some radiant heat, adding another layer of complexity to the overall heat transfer calculations. It's not just clear air anymore when steam is present.
Got it. Moving on from the stove itself, let's talk about air circulation and temperature stratification. That leads to those distinct vertical temperature gradients we all feel in a sauna, hot up top, cooler down low.
Right, and that starts with the fact that even the most well-built sauna isn't perfectly sealed. It always leaks heat and air. Typically, you'll see a small but continuous loss of hot air, maybe half a full air change per hour, or about 1/3 of normal ventilation flow, mostly sneaking out around the door seams.
Unintentional ventilation.
Exactly. This means heat is constantly escaping through natural convection. Hot air leaks out high, cold air leaks in low. And of course, dedicated ventilation, whether natural or forced, also contributes significantly to heat loss, as warm air is intentionally exhausted and cooler air drawn in.
So the warmer air rises, making the top of the sauna hotter than the bottom. That's why the upper benches are always the hottest spot.
Precisely. This creates a distinct vertical temperature gradient. Now, the temperature isn't perfectly uniform horizontally. Either complex three-dimensional air movements driven by fluid mechanics create varied temperature fields. But the primary gradient is always vertical. It's physics. Thermal expansion of gases causes buoyancy. Hot, less dense air rises. Cooler, denser air sinks.
And how you ventilate makes a difference here, too.
Absolutely. The placement and type of ventilation openings, whether natural or mechanical, further influence and complicate these air movements. For instance, benches with small gaps, maybe 1 centimeter, and spaces between benches and walls can promote better air movement and temperature homogeneity somewhat, though their impact on air stratification is probably less pronounced than for steam distribution.
And in the real world, a sauna never truly reaches a perfect, steady state where temperatures are perfectly constant, does it? It's always fluctuating a bit.
Not entirely, no. While we discuss steady states in theory, where temperature doesn't change over time, in practice, electric stoves cycle on and off based on their thermostat, causing minor temperature variations of maybe a few degrees. Wood stoves, by their very nature, are even more dynamic, never truly operating in a steady state due to the variable nature of combustion.
But we can talk about typical ranges.
Oh, definitely. We can observe general temperature ranges. For a typical Finnish sauna, say 20 cubic meters in size and maybe 2.3 meters high, with a 15 kilowatt electric stove, you might experience temperatures around 40 degrees C. That's 104 Fahrenheit right at the floor.
Pretty cool down there.
Relatively, yeah. Then it climbs to about 60 degrees C, 140 degrees airfit at the foot bench. maybe 90 degrees, 194 degrees air. At the main bench where you sit, 100 degrees C, 212 degrees F at head level, and it could be up to 115 degrees C, 239 degrees air right at the ceiling. That's a huge difference from top to bottom.
Wow, yeah, a 75 degrees Celsius difference.
Exactly. And this highlights a core principle. The thermal environment within a sauna is far from uniform. It's a dynamic system where every single design choice, from the stove type and placement to the bench height and ventilation strategy, influences how heat moves and ultimately how you experience it. The goal is often to manage rather than completely eliminate these gradients, allowing for different levels of heat intensity within the same space.
Okay, now let's talk about us, the sauna goers. Our experience of that heat is incredibly personal and subjective, isn't it? It's not just about the absolute temperature on the thermometer. What feels hot to one person might be just right for another.
That's absolutely right. Human heat sensation, what we often call felt temperature, is a really complex concept and honestly not always precisely defined scientifically. It depends on much more than just the absolute temperature of the air.
Like what?
Well, factors like the type of fluid air versus water, for example, the nature and speed of convection, is the air still or moving? Humidity levels, how long you're exposed, and even psychological factors all play a significant role. This is why a 90 degrees C dry finish sauna feels completely different from, say, a 50 degrees C Turkish bath or steam room, despite both being definitely hot.
And those vertical temperature gradients we just talked about must play a huge role in comfort. You're trying to achieve a comfortable balance between your head and your feet, right? And no one scorching ears and freezing toes.
Exactly. That ruins the experience. For optimal comfort, ideal head-to-feet temperature differences are often cited as being around 15% of the head temperature in Celsius. So for example, if it's 90 degrees C at your head, roughly 77 degrees C at your feet would be considered ideal by some metrics.
Okay.
Differences of around 20% are considered good, and even up to 27%, like 90 degrees C at a head, maybe 66 degrees C at the feet, can still be acceptable for a comfortable thermal gradient.
Where do these numbers come from?
It's worth noting that these rules primarily come from Walker Angels Trumpkin's notes, and they're based on subjective participant feedback. They actually allow for steeper gradients than standard building comfort norms, but of course, those norms are for everyday living conditions, not the extremes of a sauna.
Okay, let's unpack this. So while Angel's rules are a great starting point for thinking about comfort, they also remind us that the perfect sauna experience is deeply personal and maybe still a bit of a frontier for scientific exploration. We're trying to bridge subjective feeling with objective measurement. And I also saw some interesting critiques in our sources about just looking at percentages of Celsius temperatures. That doesn't sound quite right physically.
You're astute to pick up on that.
Okay.
Yeah, using percentages on Celsius temperatures can sometimes be misleading because the Celsius scale doesn't start at absolute zero, so the ratios don't represent energy ratios directly. A more physically sound approach, as suggested by some researchers, would be to look at relative standard deviation of the temperature elevation compared to outside, or even better, to focus on the total heat flux experienced by the body.
Heat flux again. So how much heat is actually hitting you?
Exactly. Combining both convection and radiation rather than just looking at air temperature alone. This moves beyond simple air temperature readings to a more comprehensive understanding of the total thermal load on your body.
Does the type of stove matter for the gradient?
It seems to. We also see that stove type can influence this gradient. Some experiments have shown wood stoves can sometimes create smaller head-to-feet temperature differences, maybe 20-23 degrees C, compared to electric stoves, which might generate larger gradients, perhaps 40-45 degrees C, especially if the electric stove is raised higher. Being positioned higher in the sauna yourself on higher benches can also naturally help reduce the perceived gradient because you're moving your feet up into warmer zones.
Okay.
Precisely. So this raises an important question. How do we quantitatively assess comfort in such extreme environments? We really need to move beyond simple temperature readings to the total heat flux experienced by the body, combining both convection and radiation. This is where future research can really shine, giving us a more complete picture of what comfortable truly means in a sauna environment.
Now, let's dive into what for many is the very core of the sauna experience. Lowly, the art and science of steam. It feels almost magical when that wave hits you, but it's pure dramatic physics, right?
Absolutely.
And
And it is dramatically powerful physics. When water is thrown onto hot stones, it very rapidly heats from ambient temperature up to 100 degrees C, the boiling point, and then it vaporizes, turns into steam. This water vapor is significantly less dense than hot air, about 36% less dense at 100 degrees C, causing it to rise very rapidly.
that rises fast. Then what?
The critical part is what happens next. As this vapor hits the relatively cooler skin of occupants, your skin is typically around 34 degrees C. In a sauna environment, it immediately condenses back into tiny liquid droplets
Right on your skin.
right on your skin. And this condensation process releases an enormous amount of latent heat, that hidden energy we talked about. This heat is transferred directly to your skin, making you feel an intense, enveloping warmth almost instantly.
Here's where it gets really interesting. The sheer power involved in creating that loyalty is colossal. It's far more than the stove itself is putting out at that moment.
It truly is. Vaporizing just one usual ladle of water, maybe 0.2 kilograms or so, requires approximately 518 kilojoules of energy. If this vaporization happens rapidly, say in just 1 to 5 seconds, the instantaneous power released is an astonishing 103 kilowatts, up to 518 kilowatts.
Oh, compared to a normal stove.
To put that in perspective, this is like having 10 to 100 typical sauna stoves, which might be 310 kilowatts, firing all at once just for those few seconds.
Where does all that power come from?
This immense power isn't generated by the stove in that moment. It comes from the energy slowly accumulated and stored beforehand in the massive thermal battery of the stove's structure, and especially the stones. It's a rapid transient release of stored energy, which is why you can't just continuously throw ladle after ladle without the stones eventually cooling down below the vaporization point.
So it's not just that the air gets momentarily hotter. There's a multi-pronged assault on your senses when loyalty happens. It feels different.
Indeed. Several factors contribute to the increased felt heat during loyalty. First, the steam itself may actually be hotter than the surrounding ambient air, especially right off the stones. Second, the rapid vaporization causes a sudden expansion of gas, creating significant air movements and local forced convection.
Like a puff of air hitting you.
Exactly. It's like a mini fan effect, increasing the convective heat transfer to the skin, similar to how a convection oven cooks faster by circulating hot air. But the primary reason for the intense sensation is, as we discussed, the massive amount of latent heat released over 2,200 kilojoules per kilogram of water as steam condenses directly on your cooler skin. That condensation heat transfer is the dominant mechanism for that intense thermal shock, that punch.
And the magnitude of this heat flux, the rate of heat hitting you, can actually be dangerous if not respected.
It can be, yes. This condensation can dramatically increase the heat flux received by a person from a baseline of around 300-600 watts per square meter to a staggering 3,000-6,000 watts per square meter. That's potentially up to 6 times the maximum solar flux you'd experience from the sun at noon.
6 times the sun. Wow.
This level of flux can cause pain or even burns in mere seconds or tens of seconds, which is consistent with user experience in scientific curves, like the Stoll curve, for thermal pain and injury. Now, these are transient fluxes, of course. Continuous exposure to such levels would be unbearable, equivalent to being in a cooking oven at nearly 200 to 275 degrees Celsius. It's extremely dangerous if prolonged.
Right, it's a quick burst. And when we see what we call steam, is it truly pure water vapor? You mentioned vapor is invisible.
That's right. Pure water vapor is actually invisible. What you might see visually are unvaporized water droplets that got splashed, or suspended liquid water, or perhaps recondensed fog tiny liquid particles forming in the slightly cooler air away from the stones. Steam, technically, at normal atmospheric pressure, is 100 degrees Celsius. Superheated steam is steam above 100 degrees Celsius.
Can you get superheated steam in a sauna?
Well, some steam near the very hot stones, which can be 260, 310 degrees C, might be partially superheated, but it usually cools down quite a bit through mixing before reaching the occupants, which is thankfully much safer. You don't want 300-degree steam hitting you.
Definitely not. I've also heard about adding things like menthol or eucalyptus to the water. How does that play into the sensation?
That's interesting. Adding essential oils like menthol to the water can, paradoxically, create a sensation of coolness in mucous membranes like the eyes, nose, and mouth due to how menthol interacts with cold receptors. This contributes to a unique, intense hot and cold experience that many find exhilarating.
Important safety tip, though.
Yes, very important. Always dilute these oils in the water first, or use a diffuser. Never pour them directly onto the hot stones, as they can burn, smoke, and release potentially harmful compounds. And speaking of water, using clean water like regular tap water is crucial. You definitely want to avoid toxic or corrosive substances. Also, pour gently onto the stones. Don't splash violently to prevent scalding splashes and potential electrical hazards with electric stoves. What's truly fascinating here, I think, is that the intense heat we feel during loyalty isn't simply hot or air. It's a multifaceted physical event dominated by the immense latent heat release of steam condensing directly on our skin. It's a controlled, powerful burst of thermal energy, masterfully delivered by the interaction of water, superheated stones, and our own bodies acting as condensation surfaces.
It's applied physics you can feel. Okay, beyond the heat itself, breathing easy and comfortably in a sauna is paramount for both health and enjoyment. This brings us to ventilation, which you mentioned is absolutely essential.
It's critically important, yes. Ventilation is key for both air renewal, getting fresh air in and stale air out, and managing the sauna's thermal environment, influencing those temperature gradients we talked about. While official standards and recommendations can vary a bit,
What's the general idea?
the core insight is that your sauna needs significant continuous air exchange, probably far more than you might intuitively think to keep the air fresh and healthy. Think of it this way. You need enough airflow to completely replace the sauna's entire volume of air several times every hour.
Several times. Wow.
Yes. For instance, recommendations often range from 3 to 8 complete air changes per hour, ACH. Some sources, like the EN 15821 standard, suggest around 6 volumes per hour. Others might recommend 7.2 cubic meters per hour per square meter of floor area. And small saunas often need even more, maybe 8 ACH, typically requiring mechanical ventilation because natural airflow might struggle in a small space.
And the main reason for this constant air exchange is to maintain good air quality, particularly by diluting carbon dioxide, right? When you have multiple people breathing in a small, hot, enclosed space, CO2 must build up really quickly.
Exactly. That's the primary driver for air quality. Outdoor CO2 levels are typically around 400 parts per million ppm. Good indoor air quality is generally considered to be between 600 and 1,000 ppm, and a target of about 700 ppm is often suggested for saunas to ensure comfort and avoid that stuffy feeling.
What happens if CO2 gets too high?
Well, CO2 itself is generally harmless up to maybe 10,000 ppm, but concentrations above that become unpleasant, making breathing feel heavy or labored. Above 20,000 ppm, breathing can become significantly strained. Above 100,000 ppm, that's 10%, visual disturbances and tremors can appear, with possible loss of consciousness. And above 25%, well, that can be fatal.
Okay, so ventilation is definitely a health issue.
Absolutely. An adult at rest breathes about 6 liters of air per minute, but that increases significantly with activity or heat stress. So maintaining adequate air exchange, often recommended around 9-12 liters per second per person, is vital for comfort and effective CO2 management.
So, to put it simply, it's not just about getting hot, it's about having a healthy, breathable environment, and that means managing airflow is paramount. But all this ventilation must come at an energy cost, right? You're constantly throwing hot air out.
It absolutely does. Ventilation is, in fact, the primary source of heat loss in a well-insulated sauna. It significantly increases energy consumption, potentially by hundreds of watts or even more, as you continuously exchange that hot indoor air for cooler outdoor air. This makes ventilation strategy a crucial factor in both the design for comfort and the operational costs.
Given its importance, optimizing vent placement must be a real art. It's not just drilling a couple of holes. What are the best approaches for making sure the air moves efficiently and comfortably?
It's definitely more than just drilling holes. Traditionally, fresh air inlets were often placed low down near the floor, and hot air outlets were placed high up, often on the wall opposite the stove. The idea was to encourage a simple, rising air circulation pattern based on natural convection.
Makes intuitive sense, but maybe not optimal.
Maybe not always. Modern recommendations, often backed by computational fluid dynamics simulations, frequently suggest placing the fresh air inlet at the same level as, or even higher than, the stove, ideally directly above it, feeding cool air into the rising hot air plume.
Why is that better?
This approach can lead to significantly better air mixing throughout the entire sauna volume and can help to reduce thermal stratification, meaning less difference in temperature between your head and your feet. A very high inlet near the ceiling can further aid that mixing process, driving the fresh air down more effectively.
So there's a big difference in how these vent placements work depending on whether you have natural ventilation just relying on temperature differences or forced ventilation with a fan.
A critical distinction, yes, absolutely critical. Forced or mechanical ventilation uses fans to actively move the air. With this system, the best mixing is often achieved with that high or very high inlet and a low, ideally opposite, extraction point, outlet. This creates a powerful top-down airflow pattern that actively combats stratification and ensures consistent airflow regardless of external conditions like wind.
Okay, so mechanical gives you more control. What about natural?
Natural or gravitational ventilation relies solely on the buoyancy of hot air rising. If you introduce fresh, cool air high up with only a natural system, that cool incoming air doesn't have much incentive to descend. It might just hang out near the ceiling, leaving the lower parts of the sauna relatively cold and poorly ventilated. And conversely, if both the inlet and outlet are placed low down, you can create a short circuit, where fresh air comes in low and goes straight out low, effectively ventilating only the bottom section and leaving stale, unrenewed air up where the occupants actually are.
So natural ventilation is trickier to get right for good mixing.
It is. It's a trade-off. While mechanical ventilation offers superior control for achieving temperature homogeneity, many people still prefer the absolute silence and simplicity of natural ventilation. There's no fan noise.
And where should the air exit? You don't want to lose all that precious loyalty right away when you throw water on the stones, do you?
Precisely. That's a key consideration for the loyalty experience. The air outlet should not be placed right at the very top, as this would quickly suck out the rising steam cloud and diminish the intensity and duration of the loyalty. A low outlet, often positioned under the benches, is commonly used in many designs.
Why under the benches?
The idea is to draw out the cooler, denser, potentially CO2-rich air that sinks to the bottom without immediately pulling out the rising steam from above. Some designs also include a second, closable high outlet which can be opened after the session for complete post-sauna aeration to air out the space thoroughly.
Sounds complicated. Are there other tricks?
Well, having multiple, perhaps closable, inlets and outlets, positioned strategically around the sauna's perimeter and maybe oriented differently, can also significantly improve temperature homogenization. And some modern stoves or dedicated systems, like the Sauna heat equalizing system mentioned in the sources, even include fans to actively mechanically circulate air within the sauna to homogenize temperatures. One experiment showed such a system could reduce a huge ceiling-to-floor temperature difference from 60 degrees C down to just 30 degrees C.
That's a big improvement.
It is. It's also interesting to note that older, traditional saunas with their less airtight log construction often had quite effective natural ventilation and mixing, simply due to their inherent leakiness. Air could just find its way in and out through the gaps. Of course, this came at the cost of much higher heat losses and energy consumption.
So what does this all mean for someone designing or even just using their own sauna? It's clear that the placement of these invisible air pathways, the vents, is far more critical than you might initially imagine for achieving both comfort, good air quality, and a true satisfying, lowly experience.
This really raises an important question about balancing optimal thermal performance and air mixing with the traditional silent experience many still prefer from natural ventilation. Especially given the ongoing debate and sometimes conflicting advice you see in the sauna community about the correct vent placement. It's definitely not a one-size-fits-all solution, but understanding the underlying physics helps you make much more informed choices for your specific situation.
Speaking of traditions, there's a famous Finnish principle known as the law of steam, attributed to the ethnographer Sakari Pelsi. What's that all about? Sounds quite grand.
It does sound grand, doesn't it? This empirically established Finnish law, or perhaps more accurately rule of thumb, suggests that for optimal enjoyment and to be truly enveloped by the rising steam, a bather's feet should ideally be positioned higher than the top surface of the stove stones.
Feet above the stones. Okay. What's fascinating here is that this traditional rule seems to have a strong physical basis. It's not just folklore.
It absolutely does, as we've discussed. Hot gases naturally rise, and water vapor is even lighter, even more buoyant than hot air, about 36% less dense at 100 degrees C. This makes steam highly prone to stratification. It really wants to rise and stay at the very top of the sauna.
Creating a steam layer up high.
Exactly. This can create a distinct segregation of the hot, steamy air above the level of the stones and the somewhat cooler, drier air below. Pelsi's rule basically says, get your whole body up into that steam layer for the best effect. Numerical simulations using CFD have actually validated this stratification phenomenon, confirming the physical logic behind his observation from decades ago.
But is it always practical? Can everyone always get their feet above the stones?
That's the catch. This law isn't always achievable in practice, especially in saunas with lower ceilings or those using very tall column-like stoves where the stones reach quite high. There are also practical limits on bench height for comfort and safety minimum, and maximum bench-to-ceiling heights, typically around 100 to 120 centimeters, about 40-47 inches, are generally recommended to provide adequate headroom and avoid uncomfortable drafts near the ceiling.
Are there benefits to taller saunas, then, in relation to this?
Yes, taller saunas can have some advantages. They naturally allow for higher benches relative to the stove. Plus, Taller ceilings mean cooler temperatures down at door height, which can lead to less heat loss, particularly when the door is opened. It also potentially reduces heat loss through windows if they aren't placed too high up.
So while stratification, that temperature difference, is often seen as something to combat for homogeneity, it can actually have a dual nature, maybe even be desirable sometimes.
Absolutely. While engineers often focus on reducing stratification for uniform conditions, some users genuinely prefer it. It allows for a natural range of temperatures within the same sauna intense heat for those who want it on the upper benches, and lower, milder conditions for children or those who prefer a gentler experience on the lower benches, all achieved with the same heating power input.
Does the stove design affect stratification?
It might. Some sources suggest a closed stove design might lead to more pronounced segregation of the steam layer compared to an open mesh-type stove, although research looking at temperature and air velocity fields shows mixed results. An open stove might allow steam to escape more broadly rather than just straight up. Ultimately, the law of steam should probably be seen as a useful recommendation, a target to aim for if possible, rather than an absolute unbreakable rule, especially since modern ventilation strategies also significantly impact how steam is distributed throughout the room.
Right. Ventilation complicates things. And finally, let's quickly touch on air leaks again. They're inevitable, aren't they? No sauna is perfectly sealed no matter how well it's built.
You're absolutely right. No sauna is perfectly airtight. Leaks always exist, whether it's tiny gaps around the door and windows or through the natural porosity of the construction materials themselves, like wood. Even a sauna built to be hyper airtight will still exhibit some minimal air exchange due to leakage.
How much leakage are we talking?
Well, studies have measured air change rates. For example, a sauna might have 6 to 8 air changes per hour, ACH, with the ventilation system fully open. But even when the vents are completely closed, it might still show 2-3 ACH just from residual leakage. Even a meticulously sealed test sauna showed leakage rates between 0.08 and 0.5 ACH. So it's always there to some degree.
What actually drives these leaks in a hot sauna? Is it just air sneaking in randomly?
There are two main drivers for this leakage flow. First, there's the chimney effect, also known as the stack effect or thermosiphon. The warmer, less dense air inside the sauna creates a slight positive pressure higher up and a slight negative pressure lower down compared to the outside. It's like a natural exhaust fan. Hot air pushes out through upper leaks while simultaneously drawing cooler outside air in through lower leaks. The whole sauna essentially acts like a giant, albeit leaky, thermosiphon.
Okay. And the second driver?
Second, for outdoor saunas especially, wind pressure plays a significant role. Wind blowing against the building exerts dynamic pressure, literally forcing air into the sauna through leaks on the windward side and sucking air out through leaks on the leeward side. A moderate wind, say around 33 kilometers per hour, about 20 miles per hour, can generate a motive pressure of 50 pascals, which is enough to create noticeable airflow through even small gaps.
And the leak rate isn't constant.
No, the actual leakage rates tend to increase non-linearly with the pressure difference, meaning the stronger the wind or the bigger the indoor-outdoor temperature difference, which drives the chimney effect, the more air will leak in and out. The exact relationship depends on the size and nature of the openings.
This raises an important practical question. Since leaks are always there, should we just rely on them for ventilation instead of installing proper vents?
Absolutely not. That would be a mistake. While leaks are unavoidable, they are completely insufficient to provide the adequate ventilation needed for good air quality, which, as we said, requires maybe 3 to 8 complete air changes per hour. Leaks typically provide much less than that. They're also incredibly inconsistent if there's no wind-driven flow, and the chimney effect alone usually isn't strong enough, especially in milder conditions, to guarantee the necessary air renewal.
But they matter for heating.
Yes. Crucially, however, these unavoidable leaks must be factored into the total heat loss calculation when you're sizing the stove's power. Ignoring the heat loss through leakage would mean your stove might be undersized and struggle to reach or maintain the desired temperature, especially on cold or windy days. So leaks don't replace ventilation, but they do contribute to heat loss.
Got it. Okay, now that we understand how heat moves and how air circulates, let's consider the physical structure of the sauna itself. Material science plays a huge role in both comfort and safety. Let's start with a warning. Why is metal such a menace in a sauna? Everyone knows not to touch the hot stove, but you often hear warnings about even jewelry, like a metal ring or necklace.
Yeah, metal should generally be avoided for surfaces you might touch in a sauna, especially things like door handles or exposed bench fasteners. The reason lies in a crucial thermal property called thermal effusivity.
Effusivity. That sounds technical. What is it?
Think of effusivity as a material's inherent ability to communicate its temperature to another material it touches, or maybe more simply, how quickly and effectively it can transfer heat to something else, like your skin, upon contact. Steel, for example, has a much higher thermal effusivity than wood, like maybe 20 times higher.
20 times. Wow.
Yes, this means metal, with its high effusivity, transfers its heat energy to your skin far more effectively and rapidly than wood does, causing that sensation of intense heat, pain, or even burns much more easily, even if the metal and the wood are at the exact same air temperature.
So, to reiterate, maybe a metal ring that's been on your finger the whole time might be okay because your body keeps it relatively cool through blood flow, but a metal pendant that's been dangling freely in the hot air could be really dangerous because it's reached the full air temperature and will dump that heat into your skin almost instantly if it touches you.
Precisely. That's a great distinction. A ring or watch in constant intimate contact with your skin is often thermoregulated by your body's circulation, keeping it at a relatively stable, comfortable temperature close to skin temp. The real danger often comes from items like necklaces or pendants that hang away from the skin. They heat up significantly to the ambient air temperature and then can cause nasty burns upon accidental contact precisely because of their high effusivity. They transfer that stored heat very efficiently.
This raises an important question then about how we perceive temperature. It's not just the temperature reading of an object, but how quickly and effectively it can transfer that heat to our skin. Effusivity explains that difference so well.
Exactly. It's why a wooden bench feels warm and safe to sit on, even at 90 degrees C air temperature. But a metal handle at that same temperature would almost instantly burn you. It's all about the rate of heat transfer on contact.
Okay, so avoid metal. Let's delve into the key thermal properties of the materials we do want in a sauna, the ones that make it such a comfortable and unique environment. Wood, obviously.
Of course. Wood, the most common material for benches and wall paneling, is almost perfect for sauna interiors. It typically has a low density, a relatively high specific heat capacity, meaning it can store a fair bit of heat per kilogram, and crucially, very low thermal conductivity and low thermal effusivity.
Low conductivity and low effusivity.
Yes. This combination means it doesn't quickly conduct heat away from your body when you touch it cold, nor does it quickly push heat into your skin when it's hot. So it always feels relatively warm and, most importantly, safe to touch, even when the air temperature around it is very high.
What about the stuff behind the wood, the insulation?
Right, the insulation, typically materials like rock wool or glass wool, or sometimes specialized rigid foams like PIR, it's crucial. These materials are hidden behind the wood paneling, and their job is to have extremely low thermal conductivity, even lower than wood, and very low effusivity. This is vital for minimizing heat loss through the sauna walls, floor, and ceiling, keeping the heat contained efficiently.
And the sauna stones, they're special too.
Yes, sauna stones, typically dense volcanic types like steatite, soapstone, olivine, or sometimes granite or basalt, are essentially designed as heat batteries. They have a high density, a moderate specific heat capacity, quite high thermal conductivity compared to wood or insulation, and relatively high effusivity.
Why is that combination good?
This makes them ideal for absorbing and storing large amounts of heat from the stove, and then rapidly releasing that heat when needed, especially for that dramatic vaporization of water during loily. The high conductivity helps heat penetrate the stone, and the high effusivity helps release it quickly to the water.
And then there's the steel used in the stove structure itself.
Right. Steel, typically used for the stove body and firebox, has a very high density, a somewhat lower specific heat capacity than stone, very high thermal conductivity, and extremely high thermal effusivity.
How does steel compare to stone for heat storage?
Interestingly, if you compare equal volumes, say a cubic foot of steel versus a cubic foot of stone, at the same temperature, the steel actually stores about 60% more energy because it's so much denser. However, if you compare equal masses, say 20 kilograms of steel versus 20 kilograms of stone, at the same temperature, the stones actually store about 96% more energy because their specific heat capacity is higher. This shows why a good mass of stones is so important. It's not just about volume. Mass matters for heat storage capacity.
Okay, so the stones themselves are a vital component. They're not just decorative rocks sitting there. They're the functional heat battery for the loyali and for helping maintain the sauna's overall temperature stability.
Absolutely central to the function, yes. Sauna stones are usually volcanic, as mentioned, though artificial ceramic stones also exist now. They typically come in sizes ranging roughly from 4 to 8 centimeters, or maybe 10 to 15 centimeters in equivalent diameter.
How should they be placed in the stove?
It's important not to pack the stones too tightly together, as this can restrict airflow through the stone mass, hindering convection and potentially slowing down the heating process. However, packing them excessively loosely might exacerbate vertical thermal gradients within the stove itself. Finding a good balance is key. Also, stones deteriorate over time.
They break down.
Yes, they experience thermal shock every time water hits them, and physical stress from heating and cooling cycles, causing them to fragment. They need occasional inspection and replacement, maybe every few years depending on use. And it's always recommended to clean and dust them thoroughly before the initial installation.
And safety is paramount here. I've heard horror stories about people just grabbing rocks from a river or their backyard and putting them in the sauna stove. That sounds like a terrible idea.
It's a critical safety point. It's an extremely dangerous idea. Only use stones specifically designed, tested, and certified for sauna use. Random nature stones can contain hidden moisture pockets or minerals with different expansion rates. When heated rapidly, these can cause the stones to explode violently due to thermal shock.
Explode.
Seriously, literally explode, sending hot fragments flying. Or they might release toxic vapors when heated. Both pose serious health and injury risks. It's just not worth the risk. Proper sauna stones are selected for their thermal stability.
How hot did the stones actually get?
The stones in the stove can reach quite high temperatures, maybe around 260–310 degrees C, that's 500–590 degrees thereaf, near the heating elements or fire. Temperatures will vary within the stone mass, perhaps from 50 degrees C at the very bottom to 300 degrees C or more at the hottest points. Crucially, they must be heated to at least 100 degrees C, 212 degrees air, to effectively vaporize water for low-leak.
And how much water can they handle?
To give you a sense of scale for steam generation, with an average stone temperature of about 200 degrees C, 1 kilogram of typical steatite stones can store enough energy to vaporize about 0.087 kilograms of water, about 3 ounces. So a typical stove holding 25 kilograms, 55 pounds of stones, could theoretically vaporize over 2 kilograms, about half a gallon of water, before cooling significantly. A larger stove with 80 kilograms, 176 pounds of stones, could vaporize almost 7 kilograms, over 1.5 gallons. That shows their immense heat storage capacity.
So when it comes to adding water for Luli, less is definitely more for safety and maybe just practical. Don't be tempted to douse the whole thing at once.
Indeed. That's the key takeaway for using Lursley safely. Only pour 1 or 2 ladles, maybe 0.2 kilograms, about 7 ounces of water, at a time. Pouring excessive amounts of water, especially if the stone mass isn't hot enough or large enough to vaporize it all quickly, risks creating boiling water runoff and generating large clouds of scalding steam, which can cause severe burns. Always pour gently onto the main body of stones, not splashing wildly, to avoid these splashes and also potential electrical hazards with electric stoves if water gets where it shouldn't.
Right. Okay, now let's look at the different stove types. The classic wood-burning stove versus the modern electric stove. Each has its own distinct character and practical trade-offs, doesn't it?
They certainly do. Wood stoves, or kiwas as they're called in Finnish, offer that traditional, arguably more rustic experience. Many people appreciate the authentic wood fire smell, the soft, flickering light, and often perceive it as having more soul or connection to tradition.
How efficient are they?
Efficiency varies. Older models might have been only 30–60% efficient in transferring heat to the sauna rather than up the chimney. Modern wood stoves are much better, achieving around 65–85% efficiency in standardized tests, typically around 70%. However, it's worth noting that real-world efficiency might often be closer to 50% due to non-ideal operating conditions, like how the wood is loaded or the air controls managed, compared to controlled lab tests. The EN11 High 8201 standard, for instance, requires at least 50% efficiency for certification.
How do they work?
They work by combustion of wood, specifically the volatile gases released during pyrolysis. Importantly, wood stoves require a dedicated fresh air intake, often a 10-centimeter, 4-inch diameter pipe leading directly to the firebox, specifically for combustion air. This should be separate from the general sauna ventilation system to avoid drawing already heated sauna air into the fire and unnecessarily cooling the sauna.
And the heat output isn't constant.
No, not at all. The power output from a wood stove is highly variable throughout the combustion cycle of a batch of wood. You typically see a growth phase, a stationary phase where it's burning hottest, and then a decay phase as the wood burns down. This whole cycle might take 60–90 minutes. The peak power output during the hot phase can be significantly higher, maybe 30% to 100% higher than the stove's average nominal power rating.
And a lot of heat goes up the chimney.
Yes, a significant amount of heat is inevitably lost through the hot flue gases exiting the chimney. These gases can be flowing at 15–25 grams per second at very high temperatures, maybe 375, 510 degrees C, 700, 950 degrees Fair, or even hotter peaks. This represents thousands of watts of energy loss.
Okay, so wood has character but is maybe less efficient and less consistent. What about electric stoves? They seem like the convenient option.
Yes. Electric stoves are generally prized for their convenience and simplicity. There's no fire to build or tend, no wood to chop or store, no ash to clean up. They're often remote controllable, sometimes even via smartphone apps, allowing you to preheat your sauna.
And efficiency.
Their energy efficiency in converting electricity into heat within the sauna itself is close to 100%. Virtually all the electrical energy consumed is turned into heat inside the room, though overall energy efficiency depends on how the electricity was generated, of course.
Do they heat up faster?
Generally, yes. Electric stoves reach their full power output almost immediately when turned on, leading to a potentially faster heating time for the sauna compared to waiting for a wood fire to establish and heat the stove mass.
How do they control the temperature?
They're usually temperature regulated by a built-in or remote thermostat. This thermostat cycles the heating elements on and off to maintain the target temperature set by the user. Often, for a 90 degrees C target, it might cycle between about 85 degrees C and 95 degrees C. External temperature sensors placed strategically in the sauna generally offer more precise and representative temperature regulation than sensors located inside the stove unit itself.
Are there other types?
Yes. There are also hybrid stoves available that combine both wood-burning capabilities and electric heating elements, attempting to offer the ambiance of wood with convenience or backup of electric.
Now, when it comes to sizing a stove, choosing the right power output, I've always heard that simple rule of thumb: use about 1 kilowatt of power per cubic meter of sauna volume. Kilowatt. But your sources suggest it's actually more nuanced than that simple volume calculation.
That rule, the 1 kilowatt hour rule, is very common and often serves as a decent starting point, especially for smaller saunas. It's practical, but theoretically it's somewhat shaky, as one source put it.
Why shaky?
Because heat loss from a room is primarily related to the total surface area of the walls, ceiling, and floor, and the insulation quality you value of those surfaces, not directly to the volume of air inside. Also, the air itself actually absorbs very little energy, maybe 3% maximum of the total energy input during the initial heating phase, compared to the energy needed to heat up the stove, the stones, the wooden structures, and compensate for losses.
So what does determine the power needed?
The required stove power is mainly dictated by the desired heating time. How quickly do you want the sauna to reach a target temperature? That's the biggest factor. Maintaining the temperature once it's hot, the steady state, actually requires much less power. Typically only 30–50% of the peak heating power needed for the initial warm-up phase to overcome the thermal mass and initial losses.
Can you give some examples?
Sure. Engineering studies provide detailed calculations for specific scenarios. For instance, a small 2.4 cubic meter sauna might only need 2.2 kilowatt to heat from 20 degrees to 90 degrees C if you're willing to wait 120 minutes, 2 hours. But a larger 8 cubic meter sauna might need 7.05 kilowatts to do it in 60 minutes, or a whopping 19.6 kilowatts if you want it hot in just 30 minutes. A very large 50 cubic meter sauna could require 54 kilowatts to heat from 0 degrees C to 90 degrees C in 30 minutes.
So bigger saunas need more power, but maybe not proportionally.
Exactly. Larger saunas definitely require more total power, but the required power density, the kilowatt per cubic meter, actually tends to decrease as the volume increases. And the key takeaway is that lower power can still achieve high temperatures if you're patient enough to wait longer for the heat up.
So if you're willing to wait a bit longer for it to heat up, you don't necessarily need the absolute biggest, most powerful stove your volume might suggest by the simple rule. And the heating process isn't linear either, right? It slows down.
Precisely. Lower power just means a longer wait. And you're right, the heating dynamics are nonlinear, typically following an exponential curve. The sauna heats up faster at the beginning when the temperature difference between the stove and the room is large, and then the rate of heating slows down significantly as the sauna temperature approaches the target temperature set point. For example, reaching 70 degrees C from a cold start of 20 degrees C might take 1 hour, but getting from that 70 degrees C up to 90 degrees could take another full hour.
Because the driving force, the temperature difference, gets smaller.
Exactly. The rate of heat transfer diminishes as the temperature gap lessens. Saunas also possess significant thermal inertia, or thermal mass, primarily due to the heavy stones, the stove itself, and the solid wooden structures.
Meaning they hold heat well.
Yes, they remain hot for quite a long time, tens of minutes to hours after the heater is turned off, especially if they are well insulated and the door and vents are kept closed. A well-designed 8 cubic meter sauna, for example, could take around 20 hours to cool back down completely to its initial cold temperature. This principle of high thermal mass is famously leveraged by traditional smoke saunas, or savu saunas. They use massive stone mounds heated for hours, which can then stay warm and provide loyally for many hours after the fire has completely died out.
Okay, this next point was a real aha moment for me from the sources. What's fascinating here is that humans, the people in the sauna, actually act as significant heat sinks. We actually cool the sauna down just by being in it. That seems counterintuitive.
That's absolutely right, and it's an important factor often overlooked in simple calculations. The human body, when exposed to ambient temperatures well above skin temperature, like 9100 degrees C in a sauna, relies heavily on sweating to maintain its core temperature and keep skin temperature down at a tolerable level, maybe 44 degrees C, 104, 111 degrees F.
How much heat does sweating remove?
Sweating can occur at a significant rate, maybe up to about 1 kilogram, 1 liter per hour per person, in intense conditions. Evaporating that sweat removes a substantial amount of heat from the body, approximately 627 watts per person, just through the latent heat of vaporization.
And we absorb heat too.
Yes. The total heat absorbed by a person in a hot sauna through convection and radiation from the surroundings can be quite high, potentially up to around 1,320 watts for a typical adult surface area. So while we're absorbing maybe 1,300 W, we're actively rejecting over 600 W via sweating. This effective pumping of heat out of the sauna environment by the occupants, converting sensible heat into latent heat of vapor, must be accounted for in stove sizing, especially if the sauna is intended to maintain temperature comfortably with multiple people inside for a sustained period.
So each person is like having an extra small heater running in reverse, taking heat out.
In a way, yes, especially considering the energy needed to evaporate the sweat. And radiation in particular contributes significantly, often more than convection, to the total heat load absorbed by the occupants from the hot surroundings. It's a complex balance.
Wow. Okay, finally and crucially, we need to talk about safety. Because a sauna is an inherently hot environment, and there are real risks if things aren't designed, built, or operated correctly. What are the absolute key considerations?
Safety is paramount, absolutely non-negotiable. For electric stoves, all electrical installation work must be performed by a qualified, certified professional electrician, using appropriate temperature-resistant cables and components rated for the high heat environment. No DIY shortcuts here.
And clearances. Keeping combustibles away from the heat.
Yes, critical clearance distances must be strictly maintained between the hot stove surfaces and any combustible materials, primarily the wooden walls and ceiling. Manufacturers specify minimum clearances typically at least 5-10 centimeters, 2 to 4 inches horizontally to walls, and maybe 1.5 meters, 3 to 5 feet vertically to the ceiling. These aren't just suggestions, they're vital requirements for preventing fires.
This raises an important question. What's the biggest fire risk, especially with wood stoves? Where do fires most often start?
You might think it's the walls right next to the stove, but often the biggest fire risk, particularly with wood stoves, is actually where the hot chimney pipe passes through the roof structure or ceiling assembly. Wood can ignite at surprisingly low temperatures after prolonged or repeated exposure to heat, sometimes cited as low as 150 degrees C, 170 degrees F, or even down to 77 degrees C, 170 degrees F over very long periods, pyrophoric carbonization. Although for short, single exposures, the ignition temperature is much higher, maybe 250, 364 degrees C.
And walls near the stove get hot.
Yes. Unprotected wooden walls near the stove can reach temperatures around 120 degrees C, 250 degrees average, so proper shielding and clearance are crucial. But the chimney is often the weak point. Chimneys must be rated for high temperatures. For example, a T600 rating means it's tested for continuous 600 degrees C flue gases, and be exceptionally well insulated, where they penetrate combustible structures. However, stove manufacturers often report average flue gas temperatures, and the peak temperatures during vigorous burning can significantly exceed these averages, sometimes by hundreds of degrees, potentially exceeding the chimney's rating or heating adjacent materials to ignition. Fire incidents related to improper chimney installation are a serious concern.
That's sobering. What about measuring the temperature? How accurate are those typical wall thermometers and hygrometers, humidity gauges we see in saunas? Can we really trust them?
That's another tricky area. Accurately measuring the true air temperature in a sauna is surprisingly difficult. Most common sauna thermometers, the dial or liquid types mounted on the wall, typically measure an equilibrium temperature. This reading is heavily influenced not just by the air temperature convection, but also by the thermal radiation they receive from the hot stove and surrounding hot surfaces. They see the heat radiating from the stove.
So they read higher than the actual air temp.
They often read higher, yes. Plus, they have thermal inertia, meaning they take time to respond to changes, causing a measurement lag. Official standards like EN 15821 actually suggest placing temperature sensors 300 millimeters, about 1 foot below the ceiling, and designing them specifically to measure only convection by shielding them from direct radiation. Other common recommendations include placing the thermometer at eye level for a seated person to get a sense of the temperature in the occupied zone.
But the cheap ones aren't that accurate.
Generally, no. Most consumer-grade sauna thermometers and hygrometers are not precision instruments. And even if you had a perfectly accurate measurement at one single point, it's only truly valid at that point, given the significant spatial temperature gradients we've discussed throughout the sauna. And critically, that single number may not accurately reflect the subjective felt temperature, which depends on the total heat flux, convection plus radiation plus condensation effects, and individual physiological factors.
What kind of sensors are used in modern ones?
Modern mercury-free liquid thermometers typically use colored alcohol. Electronic thermometers often use the thermoelectric effect, thermocouples, or resistance temperature detectors, RTDs. Hygrometers might still use traditional materials like horsehair or human hair, which physically expand and contract with humidity, or more modern electronic sensors that measure changes in electrical resistance or dielectric properties of a material as it absorbs moisture. For accurate air temperature readings, especially for research or precise control, shielding the sensor from thermal radiation is often necessary. So yeah, take those typical wall thermometer readings with a grain of salt. They give you an indication, but maybe not the whole truth.
Good to know. Okay, we've covered a lot of ground, from the microphysics of heat transfer to the practicalities of sauna design, materials, and safety. But science is always advancing. What's on the horizon for sauna research? Are people using things like computer simulations and AI?
The digital frontier is definitely impacting sauna science, yes. It's quite exciting. Scientific and engineering studies are increasingly leveraging advanced computational tools to understand and optimize sauna physics for better design, improved comfort, and enhanced energy efficiency.
What kind of tools?
It ranges quite broadly, from relatively simple spreadsheet models for basic 0D or 1D static or transient heat balance calculations, all the way up to complex 2D and 3D computational fluid dynamics or CFD software packages. Things like COMSOL, OpenFOAM, ANSYS Fluent, Siemens SimCenter, StarCCM+, WERS, or Fire Dynamic Simulator, FDS, which is often used in fire safety engineering.
What can CFD tell us about saunas?
These powerful tools allow for incredibly precise three-dimensional simulations of the complex airflow patterns, the detailed temperature fields, humidity distribution, and even the dynamic movement of steam during loyalty. For instance, FDS has been used to visually simulate how rapidly steam rises from the stones, impacts the ceiling, spreads along the walls, and mixes with the air, showing us phenomena in detail that we could never really observe directly or measure easily in a real sauna. More artistic simulations, maybe using tools like Blender with fluid dynamics add-ons, can also create stunning visualizations of these complex flows.
And there's even AI involved now. It seems like AI is getting into everything.
Yes, to some extent. There's actually a free online AI tool that's been developed called Sauna Simulator, which aims to calculate how sauna temperature evolves over time based on various input parameters like the thermometer altitude, the stove power, the sauna geometry, the mass of the stones in the stove, insulation levels, and so on. It's a neat example of how these more advanced modeling techniques are becoming more accessible, at least for estimation.
What's the next step? Where is this heading?
Well, the future directions are even more promising. A really exciting area is integrating sophisticated human physiological and thermal comfort models that simulate how the human body responds to heat, how it sweats, how blood flow changes, etc., like the Tayfair model mentioned directly into these 3D fluid dynamics simulations of the sauna environment. This promises an even finer, more holistic understanding of the complex interactions between the sauna's thermal environment and its occupants, potentially moving us closer to truly personalized and dynamically optimized sauna experiences someday. What's really fascinating here, I think, is how cutting-edge technology, from AI and machine learning to advanced computational fluid dynamics, is now being deployed to unlock the secrets of something as ancient and seemingly simple as the sauna. It's providing insights that go far, far beyond what traditional observation or simple measurements could ever tell us. Specialized resources, like the website saunaluja.fi, are actively advocating for more of this kind of engineering-based innovation in sauna design, really pushing the boundaries of what's possible.
That's really cool. Another area of interest that often comes up in conversation and sometimes confusion is the difference between infrared saunas and traditional saunas, like the Finnish style we've mostly been discussing. What's the core difference in the physics there? Is it just about how they feel?
The main difference lies fundamentally in the primary mode of heat transfer, and, relatedly, the wavelength of the infrared radiation emitted, and how that radiation interacts with your body. Infrared saunas primarily use specialized emitters, panels or lamps, designed to generate infrared radiation, often concentrated in the long wavelength or far infrared part of the spectrum, maybe around 10 micrometers wavelength.
And why that specific wavelength?
This longer wavelength infrared radiation is capable of penetrating biological tissues, like your skin and underlying muscle, more deeply perhaps 3 to 4 centimeters, compared to the generally shorter wavelength infrared radiation emitted by the hot surfaces in a classic sauna, which typically penetrates only a few millimeters. So infrared saunas aim to heat the body more directly and deeply with radiation, often at lower ambient air temperatures.
Okay, but if we connect this to the bigger picture, scientifically, isn't any thermal radiation in the temperature range of a classic sauna also technically infrared radiation? It's not like classic saunas don't use infrared heat, right? It's just a different kind, maybe.
That's a crucial technical point that is often misunderstood or misrepresented in marketing. Yes.
Yeah.
You're absolutely right. The visible light spectrum for humans is very narrow,
Right.
roughly 0.35 to 0.75 micrometers. Infrared radiation is simply defined as electromagnetic radiation with wavelengths longer than visible red light, starting from about 0.75 micrometers. Thermal radiation, the heat radiated by any object above absolute zero, generally spans a much broader range of wavelengths, typically from zero point 0.1 to 100 micrometers, which covers parts of the ultraviolet, all of the visible, and much of the infrared spectrum.
So how does a classic sauna's radiation compare?
In a classic Finnish sauna, the air temperatures might be around 90 degrees C, which is 363 Kelvin. According to Wien's displacement law, the peak wavelength of thermal emission at this temperature is around 8 micrometers. For the hotter elements like the stones, which can be 260, 310 degrees C, 533, 583 K, or the electric heating elements themselves at maybe 350, 450 degrees C, 6203, 723 K, the peak wavelengths are even shorter, maybe around 4 to 5.4 micrometers. So classic saunas emit a broad spectrum of infrared radiation, but it's generally concentrated at somewhat shorter IR wavelengths compared to far infrared saunas.
And infrared saunas are designed differently.
Yes. While the emitters in an infrared sauna can also get quite hot, maybe 300, 700 degrees C, producing some shorter wavelengths too, they are specifically engineered using materials and designs that concentrate a significant proportion of their emitted energy in that far infrared band, typically defined as 714 micrometers. The goal is to maximize the efficient deep heat transfer to the body via radiation, allowing for a therapeutic effect at relatively lower ambient air temperatures compared to a traditional sauna.
So even though both use infrared radiation fundamentally, the different wavelength profiles lead to a different heating mechanism, more direct tissue heating in IR saunas versus heating the air and surfaces, which then heat the body via convection and shorter wave radiation in traditional ones, and therefore a different feeling and physiological effect. That's why people often have strong preferences for one type over the other.
Precisely. The sensation is quite different. It's also interesting to compare sauna heat flux to solar radiation. While the maximum solar flux reaching the Earth's surface, maybe around 1,000 watts per square meter, is generally higher than the typical steady-state heat flux experienced in a traditional sauna, around 300 to 600 millimeters erg, though much higher during Lauderly, the two sensations are fundamentally distinct.
How so?
Solar radiation includes potentially harmful ultraviolet UV wavelengths and is often unevenly distributed on the body. Sauna heat, on the other hand, is primarily infrared, homogeneous ideally, and lacks UV. Crucially, in a sauna, the ambient air is usually hotter than the body's surface temperature. This actively prevents the body from cooling down through convection or radiation to the surroundings, unlike being in direct sunlight where the ambient air might be cooler and allow for some heat loss. In a hot sauna, only evaporative cooling through sweating provides significant relief for the continuous heat load.
Makes sense. And finally, let's just quickly zoom out to the broader context. How does all this deep understanding of sauna physics apply to other thermal environments or technologies around the world?
This deep understanding of heat transfer mechanisms, fluid dynamics, material properties, and human thermal response has incredibly wide applicability beyond just Finnish saunas. Take the hammam, or Turkish bath, for instance. It's often characterized by much higher humidity levels and significant condensation occurring on the skin, providing a very different kind of thermal experience compared to the predominantly dry heat and heavy sweating typical of a Finnish sauna. Understanding the physics of condensation is key there.
What about cold environments?
Absolutely. At the opposite end of the thermal spectrum, you have cryotherapy, which uses exposure to extreme cold for therapeutic effects. This also involves complex heat transfer studies, albeit focusing on maximizing heat loss from the body rapidly and safely, managing convection and radiation in very cold air or nitrogen vapor.
And looking towards sustainability.
Yes, that's a growing area too. Research is actively ongoing into designing more energy-efficient saunas, even aiming for concepts like zero-energy saunas that could potentially be fully autonomous, perhaps using stored solar hot water or other renewable energy sources to minimize their environmental footprint. It demonstrates a sustainable future for this ancient practice. So this raises an important concluding question, perhaps. How can we apply these deep understandings of heat transfer, fluid dynamics, and human thermal response to optimize not just saunas, but a wide range of other thermal environments? Thinking about buildings, vehicles, clothing, industrial processes. Anywhere where managing heat is important for health, comfort, energy efficiency, and overall sustainability. It's about taking these fundamental physical principles and using them to innovate for a better, more thermally conscious future in potentially all aspects of our lives.
That's a great point. So what does this all mean? Where have we landed after this deep dive? We've taken a truly fascinating journey today, haven't we? From the fundamental definition of temperature itself, all the way to the intricate dance of heat transfer modes, conduction, convection, radiation, phase change within the unique environment of a sauna.
We really have. We've unpacked how stoves generate and distribute heat, how the air circulates in those complex, often stratified patterns, the colossal, almost explosive power hidden within a simple ladle of water hitting hot stones during loiling.
The absolutely critical role of well-designed ventilation for both air quality and thermal management, and how the very materials surrounding you, the wood, the stones, the insulation, even the metal you shouldn't touch, fundamentally shape your entire experience and safety.
And we've even glimpsed into the future, seeing how cutting-edge tools like AI and advanced fluid dynamics simulations are now being employed to analyze, understand, and potentially refine this ancient practice, revealing the hidden science and surprising physical insights layered within every aspect of the sauna. It really is about understanding the why and the how behind the sensation you feel.
Absolutely. This deep dive has hopefully provided you, the listener, with a shortcut to being truly well-informed about the physics at play, giving you a kind of scientific lens through which to appreciate this timeless practice even more. It's about moving beyond just feeling the heat to understanding what's creating it, moving it, and how your body is interacting with it. It transforms the experience, I think.
It adds another dimension. So the next time you step into a sauna, perhaps you won't just feel the heat. Maybe you'll also sense, or at least appreciate, that intricate dance of conduction slowly warming the benches, convection currents carrying heat upwards, radiation beaming directly from the stove, and the dramatic phase change energy released when steam condenses on your skin.
Will you understand how every single element, from the type of volcanic stone selected for the stove to the precise position and size of the air vents, is meticulously orchestrating your thermal experience?
Perhaps the true perfect sweat, then, is as much about understanding the physics behind it all as it is about the simple sensation itself.
Maybe it is. It's certainly a new way to appreciate this complex yet somehow profoundly simple ritual, leaving you hopefully with a deeper connection not just to the heat, but to the elegant, powerful science that makes it all possible.